All right, hello. Today we'll be presenting the design of an automated floating station keeping power line, or AFSPL, for humanitarian aid delivery. My name is Hossein, and today I'll be joined by Alan, Amr, Nesma, and Tim. This project is a left-sided feasibility analysis of the systems engineering V model. So we'll go down the left side of the V and end with our business case. And we're going to start with the context analysis. So global humanitarian crises are increasing every year, and as a result, citizens become isolated from essential resources such as food, water, and medicine. When these disasters occur in coastal areas, cargo ships carrying humanitarian aid may not be able to dock due to piers or ports becoming inaccessible or destroyed. As a result, they must anchor themselves several miles off the shore of the disaster zone and rely on intermediate transport methods such as helicopters, trucks on floating causeways, and boats to close that several-mile gap between ship and shore. On the right side here, we have a high-level workflow showing the sequence of events that occur when there is a humanitarian disaster. First, the disaster occurs and there is a humanitarian call to action. From there, planning begins and supplies are gathered at a nearby port. Then a cargo ship anchors itself 5 miles off the disaster zone shore, and intermediate transport methods are used to close that 5-mile gap. This is our bottleneck, ultimately limiting victims receiving humanitarian aid. Advances in technology, like heavy lift electric drones, can fix this problem, but with limitations. Carrying a 1,000-pound load, they can only fly for 30 minutes before having to recharge. An alternative to batteries is the use of a catenary aerial system that allows batteries to be continuously powered. However, there is no current solution connecting power lines from cargo ships to onshore depots. Throughout the course of the project, we have conducted 13 stakeholder interviews shown on this slide and the next. And here's our ship-to-shore stakeholder transaction diagram for the as-is process. The main takeaway here is that the NGO logistics manager has extreme pressure placed on them due to multiple contradicting and competing constraints and requirements from all the other actors. Additionally, there are too many points of failure in this process, and there is a large time gap between citizens showing distress and aid being delivered.
I'm Nesma, and I'll be going over the as-is process. So here's an overview of the process. We have 3 independent processes, one for each method of transportation, whether that is the truck on the floating causeway, the helicopter, or the boat. Each process makes up 12 actors and 20 steps. So regardless of the method of transportation, each crisis starts in the same way, where a humanitarian crisis occurs and local citizens should report distress. This distress is then relayed to local governments and politicians who evaluate the situation, and NGOs who spearhead these missions to draft initial logistics plans. They consult data analysts to determine which method of transportation is optimal, and that is when each process starts to differ. So in the case of the floating causeway, because NGOs lack the necessary resources they need, they often have to collaborate with supporting military to provide those resources. Then a logistics manager can finally start planning cargo loading, and engineers would construct the causeway, and once the causeway is built, then aid can finally be transported from ship to shore via truck. There is a queue in this process to account for multiple vehicles working simultaneously because only one truck can load or unload at a time. Next is the helicopter, or the boat, which follows a similar structure with the inclusion of maritime security, who has to approve operations, adding an additional time constraint. Again, like the causeway, the truck on the floating causeway, there is a queue to account for multiple vehicles working simultaneously because there's only one place for a boat to dock. Lastly is the helicopter, and the main difference here is the inclusion of air traffic controllers who also have to approve operations before any mission can be carried out. And unlike the truck and the boat, the helicopter has 3 different landing zones to maximize for time. Overall, each process ends in a similar way, where once aid finally reaches shore, then contractors take it to distribution centers who bring it to local citizens in need. This brings us to our problem statement. So our target performance was derived from the goal of feeding 27,000 people 3 meals a day for a total of 90 days. This equals to 2.4 million food rations required. And considering that each pallet carries 720 rations, there is a need for 10,000 pallets to be delivered within those 90 days. That equals to about 110 pallets delivered per day at a cost of $400 per pallet. Comparing that target against our current methods, as you can see here, the only thing the boat succeeds in is cost, where it fails in success rate and daily throughput targets, whereas the helicopter actually exceeds success rate and daily throughput, but it's just too costly to be sustainable, and the truck fails at all metrics. All right, so no current delivery method reliably delivers 10,000 pallets to 27,000 people in a 90-day period at a sustainable cost. What if we could take those positives at a cheaper price and increased availability?
All right, moving on to our 2B process or concept of operations. Here we have our OV1 diagram showing the ship-to-shore electric heavy lift drone with the use of the AFSPL in its operational environment with a sequence flow below showing how the system operates. Our second OV diagram is a closer look at the station keeping platform and the components that it is composed of. And here is our stakeholder transaction diagram for the 2B process. As seen here, we are able to eliminate 4 actors, greatly reducing the amount of pressure that was previously placed on the logistics manager.
And moving on to our 2B process, as you can see, it's significantly condensed from 12 actors to 4 and from 20 steps to 10. So here, once a crisis occurs, NGOs quickly plan logistics and deploy the cargo ship. After a weather check is done, the AFSPL and drones are deployed, and aid is loaded directly onto drones by contractors, and then the drones travel along the power line to shore. There is a queue in this process to account for multiple vehicles working simultaneously again, and throughout the day, numerous weather checks are done. If a weather check fails, then the AFSPL and drones are recalled, and if not, it keeps working till end of day, and then it is recalled.
I'm Alan, and here's the multiple vehicle simulation model. Here's the GUI that we made for the model. Just to explain a little bit, the drones will actually be divided into 2 groups. The AFSPL actually acts as a one-way street, meaning that once one group is going, it's going to load, and it's going to come back, then the other one can leave. Here is the simulation model represented with inputs. We're going to have the number of pallets, simulation days, weather conditions, and ship-to-shore distance. And for the outputs, we're going to have the delivery time, cost, reliability, and visual representation. On the right, we're going to have the equations that actually dictate how this simulation model works. Next. Here, the most important parameter to look at is going to be the sea state limit and the wind limit, which dictate how often your vehicles work. Here, the most important parameter will be the loading time, which is the difference between a week and a day of delivery. And we're going to have 3 vehicles for each method. Here are the results. As we can see, the helicopter is the best method, having the shortest time and the best availability. However, the drone is the second best and actually manages to hit all the targets that we set at the beginning. Here we can see that the drone manages to be the cheapest option at only $234,000, with the helicopter being twice as expensive.
Hello, I am Tim. I will be going over the design of the AFSPL system here. So this is a PID controlled simulation model here, with the key inputs being the reference position and sea state level, and our outputs being settling time, steady state area, and overshoot percentage. I'm going over, this is the equation we use to model the AFSPL platform moving through water, and on the bottom there is the model architecture for the PID controller. And here is it in MATLAB. Looking at the results of this, the key takeaway here is we can close that 5-mile gap in about 71 minutes or so, but with very little overshoot percentage and steady state error. We additionally would like to test different PID values to find which one best sits higher and lower sea states respectively. And here are the results for that. And key takeaways from this one is power and rise time are the main things that the PID controls. They behave pretty consistently across sea state level, and overshoot percentage is outside of our control. Steady state error can benefit from adaptive gain scheduling, but overall the original PID values were effective across all sea states. And moving on to how we would deploy the AFSPL, we have devised 3 deployment methods. Ship to shore is basically deploying 1 unit at a time on the timer. Accordion is deploying all units at once and have them spread out to their designated location. And bidirectional is splitting the platforms into 2 groups and then having them meet in the middle to complete the line. The IO diagram for this is slightly different, with the introduction of cable parameters and tension for our outputs. And then putting this simulation into a utility function here, the accordion has the highest utility at 0.42, followed by bidirectional at 0.36. And then key takeaways again, accordion is the best, but there is some takeaways. It's a higher logistical footprint than the sequential method, and if speed is top priority, bidirectional wins by a large margin.
Hello, I'm moving on to our requirements. Starting off with the mission requirements, our first one says the AFSPL should have a top speed of 4 miles per hour. The rest of the requirements will be the next 2 slides. Moving on to the physical structure of the parts that the AFSPL consists of. Moving on to the functional parts of the AFSPL does. And then again, the functional requirements is one of the maintain alignment. The others are in the other slides. And then moving on to our verification test plan, this is what we're going to do.
All right, wrapping up with our business plan. So value proposition for humanitarian organizations. The main takeaway here is that the AFSPL can deliver 1,000 pallets within 7 days at a cost of $400 per pallet. Our projections and ROI show that even with a conservative approach, we have an ROI of over 300% and a break-even point of 3.5 years. Here is the engineering team. Thank you so much for listening to our presentation.